This is the first video that you will be watching this semester. It covers section 3.4 and it's an introduction to linear functions. It is important because functions are going to be studied throughout the course of Math 30. And so we need to get a good idea of all the terminology and how we can apply this information going forward through the semester. We're going to start out by defining what a function is, and also domain and range, which have to do with functions. We're going to talk about how to evaluate and graph functions. We're going to talk about how to interpret graphs of functions. And then we're also going to, at the end, we're going to talk about how to write a function in context to real-world applications. So starting off with our definitions here. First of all, we have a definition of what a function is. A function is a rule for which each input value is assigned one and only one output value. I like to give different examples at this point. The one that's a really good example that everybody can associate with is Social Security numbers. We all know that each person should have only one Social Security number, and so if you were to have your Social Security number as an input, then the output would be the name associated with that Social Security number. So each input can have one and only one output value. In other words, each Social Security number can have one and only one name tied to it. Also having to do with functions, we have two more definitions. We say that the set of all input values for a function is called the domain of the function, and then the set of all output values for a function is called the range of the function. Let's go back to our example of Social Security numbers. If my function, we'll call it f, takes as input, let's call it SSN for Social Security number, and then the output would be a name tied to that Social Security number. So we have Social Security number going in, name coming out. The domain is the set of all input values. So for this particular example, the domain would be all Social Security numbers in the US. And the range, which is the set of all output values, output being the names tied to those numbers, this would be the set of all, this is all people in the US with a Social Security number. And of course, there are people we know in this country that do not have Social Security numbers. They would not be included with it because their name would not come out as an output when you plugged in a number. Hopefully that example makes sense. That was an example in context of some real-world application. The next two examples also talk about the same idea of each input having one and only one output, but there's not really any context to it. It's just kind of getting used to that idea. So the first example you see, if we think of this is our input, the x is our input, and the y is our output. That's typically what we use with functions. Then we should see, in order for it to be a function, going back up here to the definition, that each input can have one and only one output. So if 6 is the input, the output is 5. If 2 is the input, the output is 3. If 4 is the input, the output is 6. And we keep going. 3 gives 1, 7 gives 6, 8 gives 6, 6 gives 5. Even though we see right here and right here, we see the same input twice. Both times we have 6 as an input, the output is still 5. So this is yes. This is a function. And since it is a function, we need to talk about what the domain and range are. So again, I'll remind you the domain is the set of all input values. So we're talking about domain, the inputs is this x column. So let's go ahead and list those as a set from smallest to biggest. The smallest being 2, and then 3, and then 4, and then 6, 7, 8. I think I got all of them. We can also list the range. That would be the second column. And if we list all those from smallest to biggest, it starts out with 1. We have 3. Then we have 5 and 6. So this is a function because each input has only one output, and then we listed the set of all possible input values and all possible output values. Let's take a look at the next example. Here again we have a column of inputs, a column of outputs, and there's a problem here. Can you see the problem that comes up with the next one that makes it not a function? Hopefully you notice, for example, this row of the table. Because we have in both rows an input of 3, but what's the output? The output in this row is 6 and this row is 7. We have the same input giving different outputs, and in order to have a function, each input can only have one output. So this is not a function. Alright, next topic I want to talk about is how do we evaluate a function. So typical notation we see here is that we have a function written as f with parentheses and an x inside, and the way we say this is we call this f of x. Sometimes students want to think of this as f times x, because that's what we usually see when we have variables next to parentheses, but this is not f times x. This is function notation, and the way we read it is we read it as f of x. And what it is it's a rule that takes x as an input and gets an output. A lot of times also we can think of y as the same as f of x. So in other words, the output value y is the same as f of x. And if we see f of x, we can think y. If we think y, we can think f of x. Just got to get used to this new terminology. So notice in general, this is f of x. This is the output for any x. In this first example, it says find the output when the input is 10, or what this is specifically saying right here is that we're letting x equal 10. And so it's pretty simple. All we do is we take 10 and we plug it into the function wherever there's an x. And a good rule of thumb when doing this is to put parentheses wherever we have an x here. So if I look at this function, it says negative 8 times x, and I'm just going to put parentheses here, plus 3. And instead of an x, what do we have? We have a 10, so we're going to put 10 here. And after you do that, all we do is simplify. Because we know that negative 8 times 10 is negative 80. We're following order of operations here, and then if we add 3 to that, this is of course negative 77. So what this says is that when you plug 10 as an input into the function, the output is negative 77. Now the next example, part B, is the same idea, but it's slightly different. We don't just have a number as an input. We have a quantity, an algebraic quantity, x plus h, but the way it works is still the same. We still have negative 8 times the input plus 3. And instead of putting a number in here, like last time we put a 10 in there, we're going to put a different input. We're going to put x plus h. And of course we could simplify this. We could distribute. We could take negative 8 times x and negative 8 times h, which would give us negative 8x minus 8h plus 3. And then we can ask ourselves if there's any like terms that we can combine. I don't see any, so this would be as far as we can go. That's your first look at evaluating functions. We are going to do this a lot this semester. We'll do it a little bit more later in this video, but I just want to introduce that concept right here at the start. Talking again a little bit more about notation. If I see this, if I see h of 5 equals -2, what we have to remember is that when it's in this form, this is x. Remember last time we had f of x in our last example, but we can have h of x, we can have g of x, we can use any variable for a function. It doesn't always have to be f, it can be h and g. In this example we have h as our function. And so what this is saying is the x value is 5, and then on the other side this is always the y value. So we could put that in ordered pair notation. We could, instead of writing h of 5 equals -2, this says that when x is 5, y is -2. You should have learned about this in Algebra 1, that in an ordered pair, the first number is always x, the second number is always y. So, if we had another example here, go ahead, how would you write this? What would come first? The x would be -11, the y would be 4. And this is how another way to think about function notation. Okay. Next we're going to talk about a specific type of function, a linear function. Linear functions have this form, f of x equals mx plus b. Now this should look familiar to you, because in Algebra 1 we talk a lot about y equals mx plus b. Remember what these parts mean. The m is the slope, and the b is the y-intercept. So let's make a little note here. M equals slope. We also, though, we like to think of slope more importantly in context of real-world applications. We can think of slope as a rate of change. We'll talk more about this in some later examples. But for right now, we'll just write it, think of it as slope, and remember that it's a rate of change. And then I already wrote right here that this point 0b, this b being the same b that's in the function form, or f of x equals mx plus b, that b is what we call the y-intercept. The y-intercept is the point 0b. So in the next example, if I say create a linear function whose graph has slope 4, is that saying m equals 4 or b equals 4? That's saying m equals 4, because it's talking about slope. And it says a y-intercept of 0 and -9. Remember, that means that this is our b, because y-intercepts always have the form 0, b. So if I were to go ahead and write this linear function, it would have the form f of x equals, what comes next? M. M in this case is 4x plus b, but b is -9. So there's my linear function. Now when we talk about functions, there's many different ways to represent a function. We can use words to represent a function. We can use algebraic rules. We're talking about algebraic rules. This right here is an example of an algebraic rule, f of x equals 4x minus 9. We can use tables. We already used tables on the first page to represent a function. We can talk about graphs to represent a function. We can use ordered pairs to represent a function. We already did that on the first page. Let's see a little bit more what we mean about these different ways to represent functions in the next example. So the example says college student takes a summer job selling newspaper subscriptions door to door. She is paid $36 for a 4-hour shift, but she also earns $7 for each subscription sold. And part A says create a linear function for the amount she earns on a shift during which she sells X subscriptions. So let's go back to linear functions, because it says that they want us to find a linear function. So that means we're going to need an M, and we're going to need a B. Remember, M is a rate of change. Or in this example, it's an amount earned that changes depending on how many subscriptions you sell. Whereas B is like the fixed earning amount. So this is the y-intercept is always a fixed amount. And in this case, it says that she's paid $36 no matter what for her 4-hour shift. So we're going to think of that 36 as the B, or the y-intercept. But then on top of that, she can add $7 per subscription. So the rate that she's earning an additional $7 per subscription. That's a rate. Rates, we always think of things as like miles per hour, dollars per ounce, feet per second. It's always one quantity per another quantity. In this case, it's dollars per subscription. And so my linear function would be f of x equals my changing part of what she earns. That's the $7 per subscription times x. X is the number of subscriptions plus $36. So it's this fixed part, but then for each additional subscription you add $7. So here's my linear function. So let's move to part B. It says using the function found in part A, find f of 2, f of 5, and f of 7. So here's a little bit more practice evaluating functions. We want to find what f of 2 is. That means we take 2 and we plug it in for what? We plug it in for x. So this first one is going to be 7 times 2 plus 36. In other words, she earns an additional $14 on top of her $36, which gives a total of $50. So if she sells 2 additional subscriptions, she earns $50 extra. Do another one. Find f of 5. F of 5 we would calculate by taking 7 times 5 plus 36. 7 times 5 is 35 plus her 36 gives $71. This says that when 5 subscriptions are sold, she earns $71. And then the last one, we're going to be finding how much the college student would earn if she sold 7 subscriptions. So the input is 7. We would take 7 times 7 plus 36, or 49 plus 36. That would give us a total of $85. Hopefully that makes sense. Now let's complete the table for the information that we just found in part B. So the first thing we found is that when our input was 2, our output was 50. And we can also remember that f of x is the same as y. These are interchangeable. So if y is 50, f of x is 50. We could write this information as an ordered pair. We could write it as 2, 50. x comma y, which is the same as writing as x comma of f of x, because y and f of x again are the same. So this would be 250. And then writing it in function notation, this says that when the input is 2, the output is 50. Remember, writing 2 comma 50 as an ordered pair is the same as writing f of 2 equals 50. And we can do the same thing with all of these three function values that we found in part B. So the next one would be 571. F of x would also be 71. This says that when x is 5, y is 71. When x is 5, f of x is 71, which means f of 5, when the input's 5, the output is 71. And you should also be able to do the next one. When x is 7, y is 85, or when the input's 7, the output's 85, which means f of x is also 85. Ordered pair would be 7, 85, or x comma f of x is 7, 85, and f of 7 equals 85. Now in part D here I wrote a different set of function values, but we should be able to put in words what this means using the context for this problem. This is that when the input is 12, the output is 120. Or when the college student sells how many subscriptions? 12 subscriptions. She earns $120 for that day. Okay, let's go ahead and now move on to part E. Part E says, let's use the table that we found in part C to graph the function from part A. So you'll remember, part C we already found a bunch of points. We found 250, 571, 785, and these have kind of high outputs, so we're going to need to label our axes accordingly. Remember, this is our x-axis. The horizontal is always our x-axis. The vertical axis is always our y-axis, so we're going to call this f of x instead of y. And then let's label these, each of these by 5. So, and I'm only going to label every other one. So this would be 5, 10, 15, 20, 30, 40, 50, 60, 70, and we'll do these by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop there. And so if we go to graph this first point, the first point says that when 2 subscriptions are sold, the amount earned is $50. So we go over here to 2 subscriptions. For X, this is subscriptions. F of X, this is dollars. So when we sell 2 subscriptions, the amount earned is $50. If we sell 5 subscriptions, the amount earned is 71. 5 subscriptions is a little bit more. It's right about there, 71. And then we just saw that 7 subscriptions is about 85. That's going to be way up here, right about there. Now, one thing we didn't find is, what about 0 subscriptions? What is f of 0? That's going to be 7 times 0 plus 36, or just $36. In other words, if you sell no subscriptions, you're just going to get your 4-hour fee of 36, which is going to put us right about there. And what we can see here is that this is a nice straight line. That's why it's called a linear function, if you will. This gives a straight line. And we could label these points. This point here is 0, 36. This was 2, 50. This is 5, 71. And the graph should kind of make sense in context there. If we start at $36, that's with 0 subscriptions. If we sold 1 subscription, that'd be 36 plus another 7 is 43. And you can see this just about crosses there at 143. And we're going up by $7 every time. We're going up by $7. So that's why the rate of change is 7. You can see that visually. You can see the slope here. So let's go ahead and move on to some graphing, a few more graphing problems. We look at the next one. It just gives us a linear function and asks us to graph it. And we can see here that the slope is going to be 8 over 3, because remember it goes mx plus b. That's the form, f of x equals mx plus b. So the slope is 8/3, and then the b in this case is going to be -2, which means our y-intercept is 0, -2. And so when we go to graph, we should have plenty of information to be able to graph this guy. Because we know that our y-intercept is 0, -2, so we start at that point. Let's label that point 0, -2. And then we have a slope of 8 over 3. A lot of times we can think of this as rise over run. You may have probably learned it that way in a previous class, which means to get to our next point, we need to rise by 8, and we need to go up 1, 2, starting at the y-intercept. We go up 8, 1, 2, 3, 4, 5, 6, 7, 8, and we run 3, or we go right 3. So and if we label this point, we always got to remember to label our points. This is going to be the point right 3, so the x value is 3, and we go up 1, 2, 3, 4, 5, 6. So this is the point 3, 6. It also says here to state the domain and range of the function. Remember, the domain is the set of all inputs, and the range is the set of all outputs. I'm going to use D and R for domain and range. This particular line, it keeps going up. But draw that arrow on there to signify that this line keeps going up, and then an arrow down here to say that it keeps going down. In other words, it's going to cover all these y values, and it's going to cover all these negative y values. It's also going to cover all these positive x values and all of these negative x values. We're going to talk more about this in future classes, but if we say that this line goes forever, both up and down and right and left, the way to talk about this domain and range-wise is negative infinity to positive infinity for the domain. Same for the range. The y values are any outputs are possible. This says any inputs are possible and any outputs are possible. Now the second example is slightly different, because in the second example there is a function here that is missing part of the f of x equals mx plus b part. What part is missing? Well, you should say there's no mx part, there's no slope. In this case, the slope equals 0, which means there's no steepness, if you will, to this graph. The graph is a flat graph. It's a horizontal line. This is the way we graph this. So if I put my axes on again, we still want to start out with our y-intercept, just like in the last example where our y-intercept was 0, -2. In this case, the y-intercept, the x is 0. X is always 0 for y-intercept, but the y is -3. So we start there at the y-intercept. We start at 0, -3. And this one has 0 slope. We don't go up, we don't run, we don't rise. We just go flat. This is a horizontal line. It has 0 slope. And this changes the domain and range. This line goes forever to the right and forever to the left, so any input is possible. Any negative x, any positive x. Domain is negative infinity to positive infinity. But the range, on the other hand, not all outputs are possible. It doesn't keep going up, it doesn't keep going down, it stays here at a constant value. What's the constant y value? Every single point on here has a y value of -3. So we're just going to list one value here for the range, or the outputs. Go over another example here. If we look at this graph, we're going to answer a couple questions about it. First example says, find what f of 5 is. Well, remembering our function notation, what we're going to remember is that when it puts the value in here, this is the x or the y? Well, you should say that this is the x. So what we're doing here is we're looking at the graph and we're going to say, okay, here's our line that represents the function, which has an infinite number of points, an infinite number of xy's. We're looking for the specific point when x is equal to what? When x is equal to 5. So if I come here along the x-axis to where 5 is, and I draw up to this line, we can see that that's the point on the line where x is equal to 5. In fact, if we label that point, that's the point 5, 4. Well, how do we write that in function notation? We've done this a number of times already. This says that f of 5 is equal to 4. Hopefully that makes sense. We can move to the next example. It says find a value of a such that f of a equals -8. Well, this is saying the exact opposite. Notice here, they're not giving us the a or the x. We don't know this. This is what we're trying to find. It's giving us the y value, right? Because it's always f of x equals y. So we need to do the opposite. We need to say, okay, well, where on this line is now x equal to -8, but y equal to -8. So if I come down here to -8 for y, that's this point, which is the point -1, -8. So if it says find a value of a such that f of a equals -8, that value of a, again, we're thinking of a as the x value, a is -1. Just to make a little note here, this is because f of -1 is equal to -8. Part C, domain and range, we already talked about this. This is just like the example above where we have a line that goes infinitely up, down, and right and left. That means that the domain and range are anything. We can have any input value, and any output value. Negative infinity to positive infinity. Alright, last thing we're going to talk about is looking at an example in context of some real-world application, just kind of interpreting functions. It says, state the quantity that is represented by both the input and the output of the function. So if I look at this function, it says the height in feet of a ball that is dropped from an 80-foot building is given by this function, where t is the time in seconds after the ball is dropped. T is the time after the ball is dropped. So if it says state the quantity that is represented by both the input of the function and the output of the function, the input, well, that's right here. We've been thinking of this as x, but it's a different variable this time. It's t. What does t represent? T is the time. So the input variable is t, which represents time in seconds. What about output? What's the y value? What do we get when we plug in time? What does this function give us as the output? We go back and look at a previous example. Remember, in this function, when we inputted subscription sold, the output was dollars. Well, in this example, when we plug in time, t, our output is h of t. What does h of t stand for? The height. The height is h of t. That's why we use h for height. So the output is the height, h of t, in feet. So this should allow us to be able to answer part B. It says using the function in part A, we can find that h of 1 equals 64. Interpret the meaning of h of 1 equals 64. Think about that for a second. It's saying, what's my input? What's my output? We know that input is time and output is the height. So this says that after how long? How much time? The input is 1. That's time of 1. So after 1 second, the height of the ball is 64 feet. Make sure you go and complete the self-check for section 3.4 notes. That's the next page. You answer all these questions, enter your answers on MyMathLab. You're going to be doing self-checks after you watch each video and bringing those to class as a reminder. Thank you. We'll see you in class.